Welcome everyone to the series of talks on combinatorial optimization problems with special emphasis on learning pedigree polytopes and the properties of pedigree polytopes and the implications of those properties. In the last two talks, we covered what is pedigree and what is meant by pedigree polytope, and we also studied what motivated me to study pedigrees. In this talk, I'll be covering one of the questions: what is the dimension of the pedigree polytope? Before we discuss what is meant by dimension of a polytope, I assume, of course, you have a basic idea on polytopes and what we mean by dimension. So I'm not going to go through the definitions of these things. But however, I will start with the dimension of the Turing polytope, because that's related to what we are studying. The result which we know on the dimension of the Turing polytope is based on, of course, the well-known or the standard formulation given by Danzig, Fulkerson, and Johnson. And in that formulation, we do have, as we discussed earlier, we have a polytope called the subtour elimination polytope. As discussed earlier, subtours are not complete tours. That means they only involve a subset of the cities and not all the cities when the tour is made. So they are subtours, and DFJ formulation ensures that we are able to eliminate those subtours from consideration by having subtour elimination constraints. So the subtour elimination polytope is nothing but the polytope described by the subtour elimination constraint, which are exponentially many. And the Turing polytope is actually contained in the subtour elimination polytope. So the dimension of the Turing polytope, it will be less than or equal to the dimension of the subtour elimination polytope. And that's where we start describing how to go for finding the dimension of the Turing polytope. So if you denote by Q sub A n to be the subtour elimination polytope, the Turing polytope, because it's actually having, that we are considering for each edge variable. So the number of variables in the problem will be n into n minus 1 by 2. So the subtour elimination polytope has a dimension less than or equal to that, and the Turing polytope will be having a dimension less than the subtour elimination, the dimension of the subtour elimination polytope. So we shall show that the dimension of the Turing polytope is actually n into n minus 3 by 2. I'm not going to go through the proof, but it's already known from the results of Groschel and Padberg. And they prove this result using an important lemma from graph theory, which talks about how to decompose the set of edges in terms of tours and some matching. I'm not going to go through the proof, and of course this can be found in the reference I mentioned and in many books on the traveling salesman problem. So now we need to consider a similar problem, but now we are discussing the pedigree polytope. So we know how we are saying, I'm just recalling what is a pedigree, which we gave based on the insertion heuristic. So we have a W which gives you the edges where 4, 5, 6, etc. up to n are inserted. This W has each component an edge that tells you where the insertion is done. So this E4 comma dot 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 F E N, that vector of edges is a pedigree. In case, of course, if you do the insertion operations, you must get a tour. Or if it's the reverse, if you take a tour and then consider where n is inserted, remove that edge, then you get a tour of up to n minus 1 cities, and you can repeat this until you get 3 tours. And of course, reversing the edges where these insertions have been done, we can get the corresponding pedigree. So that's the understanding of pedigree. Of course, I'm sure that you did also the exercises. And so we can proceed further now to see, given the corner points are all pedigrees, and then we are looking at the convex hull of these pedigrees, which is the pedigree polytope. Now, in which dimension this polytope is there? That's the question. And if you remember the formulation, MI formulation, we have n minus 3 equalities. So naturally, this polytope is going to be in that flat defined by these equalities. And it could be, the dimension should be, then of course we have of the order of n power 3 variables, that is we of course we could denoted that by tau n, actually the number of variables, that is xi, j, k's. And this tau 1 minus n minus 3, that could be the maximum dimension for the pedigree polytope. So we are using these ideas. Of course, these pedigrees are now represented by 0, 1 vectors, as we explained, that if an edge is in the pedigree, then we have 1, otherwise it is 0. And of course, we have, for each insertion, we have a corresponding 0, 1 vector from the subset of edges that are feasible. The theorem which we are going to show is that if x belongs to Pn, implies x is an extreme point of Pmin, this polytope Pmin is actually the polytope that we get from the MI formulation. This MI formulation was discussed in the earlier session, and in that we have actually we try to give a mathematical formulation for the insertion operation, and trying to find the optimal way we can insert in 4, 5, 6, etc. up to n in the optimal edges. So that's the problem, and the corresponding formulation is called the MI formulation. MI stands for multi-stage insertion formulation, and if we don't have the integer restriction, then we call that a linear relaxation or a relaxation of the MI polytope. Recall that we discussed the MI formulation for the symmetric traveling salesman problem. This is actually arising from the insertion heuristics, as I explained earlier, and we have given an 0, 1 integer formulation for the same problem. Now, in that formulation, if we relax the integer restriction, then we get what is called a PMI-N polytope. So this polytope has all the other inequality restriction and the restriction that xi,jk's are non-negative, but not the restriction that xi,jk have to be integers. So we are now, we can see that because we put into the restrictions to get the polytope, the pedigree polytope. So this pedigree polytope is a subset of this PMI-N. So that's the first thing we noticed. We now can go with the sketch of the proof. We have the n-3 equations, and together they form what's called a flat. So the PMI polytope is itself is in that flat, and so the pedigree polytope also will be in that flat. So the dimension of the polytope, as I mentioned earlier, has to be less than or equal to tau n, the number of variables in the problem, minus n minus 3. So that could be the maximum value for the dimension of this. So we'll now have to show that it is actually not strictly less than that, it's actually equal to that. Now, if it is strictly less than this tau n minus n minus 3, then we must be able to find a hyperplane, which the whole polytope is in that hyperplane. In that case, we can show it is less than that. So there must be a hyperplane of that kind, so that if we can show that, then it means that the dimension has to be less than this tau n minus 3. So this is what I'm going to do. It's not like the proof we saw for the traveling salesman problem, because we could use a graph theory lemma there. But here we had to actually produce, or we had to produce a proof that there cannot be such a hyperplane. Because then in that case we know that it has to be equal to the tau n minus n minus 3. Okay? So this goes like this. Suppose there exists such a hyperplane, then that means we have some C1, etc., Cn. For each of the component we can have a vector C1, C2, etc., Cn. And actually this starts from C4, so C4, etc., Cn. And we have to have a constant that equal to CO. So C4 X4, the capital, this boldface X4 small, and C4 X4 plus C5 X5 plus Cn, Xn is equal to C0. So that will be the hyperplane. Okay, so if we prove that there cannot be any such hyperplane, we are through. So we'll proceed in this way. We'll show that C0 has to be 0. And once we have done that, if I show C4 is 0 and we have a basis for induction, then we can proceed, say, up to Cn minus 1. If they are all 0, then Cn also must be 0, and that's how the proof will be completed. So the details, of course, you can find in the book, where we discuss about the dimension of this polytope in chapter. In this proof, we use a very simple lemma. That is, we say the existence of certain pedigrees of a particular type, and once that is proved, then we can use such pedigrees in the proof. So that's the first step for the formal proof of this. The lemma goes like this. It's called the selection lemma. Given any k belonging to b suffix n minus 3 to v3, that means any of those vertices other than the first 1, 2 and 3, that the vertices which we have in the 3 tour. So given any edge ij, e ij, that means e which has I and j as the vertices in that, belonging to e k prime, here e k prime, that means accepting the last the edge, that we say, for instance, if you have k, then it may be k minus 2 comma k minus 1. That's the last possible edge in that. So accepting that, the rest of the edges in the set e suffix k is actually 1, 2, 1, 3, etc. up to k minus 3 comma k minus 2 like that. That's how it will be. So we select a pedigree such that what we are assuring is that we can select a pedigree such that x k plus 1 e equal to 1, x k plus 1 I comma k plus 1 is equal to 1, and xl e super L are all equal to 1 for k plus 3 to n, where of course remember that we called e super L is equal to actually the last edge, that is k minus 2 comma k minus 1, or L, for L it will be L minus 2 comma L minus 1, that edge we denote it by e super L. Okay, now the proof, of course, we select a k tour and then of course insert k plus 1 in e containing obtained in a, so that actually we will, by inserting k plus 1, we can get a k plus 1 tour. So how do we choose? That is, any k tour we can take and insert k plus 1 in that, and you will get an edge where you have k plus 1 inserted in that. So naturally you will have an I k plus 1 for some I, and then in that tour we can again now take that edge and insert k plus 1 to k plus 2 in that. You get a k plus 2 tour, and now of course you will have the edge k plus 1 and k plus 2 in that. So that will be our last edge, that is e power k plus 3. So now we can extend this k plus 2 tour to a n tour, sequentially inserting L in that last edge which we have generated. So in that way it will satisfy the requirements of this lemma. So it's not very difficult, but it's simply we will understand why we have defined why do we need a pedigree like this soon. So once we have this lemma, and we have, I think, so the convex AN will be a subset of this R alpha n. Alpha n is the name we are given for tau n minus n minus 3, that is, so instead of repeating that we call it tau n, alpha n. So naturally the dimension of convex AN is going to be less than or equal to alpha n. We again use the same idea that we have to say if it is strictly less than n, then we are going to produce this one. Actually we are not doing it for the Pn, but we are doing it for this convex AN. And so the thing I already explained how the proof will be done. That is, we have to prove C4 is 0, C0 is 0 first, and then C4 is 0, etc. And that details are we will find in the proof. I think with that we can, this explanation, you can understand the dimension of the pedigree polytope is actually alpha n. Okay, so once this has been, of course, we are not going to use this until we come to the stage when we are connecting the consequences of showing the properties of the pedigree polytope, how it implies something very important in complexity theory, that is NP equal to P. So until then we don't use this, but it's a very easy thing to do at the beginning. So we have done that here.